All right. We're just a couple minutes past the hour, and looks like the majority of folks have managed to find their way to us. So I think we're going to want to look at getting started here. Um, Good afternoon, everyone. Welcome to Encore's webinar, Vision Language Models, Powering the Next Chapter in AI. Very excited to have you all here with us this afternoon. I think let's roll into, just some quick self-introductions before we get started, and then we'll move into the agenda. So once again, very pleased to be seeing you all here this afternoon. My name is Justin Sharps. I'm the head of product engineering here at Encore, making sure that all the advances in technology that people are working on in foundational AI translate their way into making all of our lives as machine learning and computer vision application engineers easier in developing production level machine learning applications. I'm joined here by my colleague, Frederick, who's the head of our machine learning department here at Encore. And Frederick, maybe you'd like to give yourself a quick introduction here.
Yes, naturally. Yeah, I'm the head of the machine learning at Encore. I take care of making sure that we are on top of what happens today, but also in like 3 months or 6 months, and that we are on top of all the stuff that we can be helping with. Now, I have a background as a PhD in machine learning, where I spent quite a lot of time looking at the autoregressive loss, which is very fortunate for this particular webinar, I guess, because that's basically going to be the secret sauce for these big models.
Yeah, thank you, Frederick. And we're all super lucky to have his time here this afternoon, a chance to pick his brain and hear about all the advances in visual language models, where we see these things going and how we can use them to advance the development of computer vision applications. So what do we have on the agenda today? Obviously, we want to just get started with a brief introduction here. And then before we get too far into things, we want to make sure we're all on the same page when we're talking about VLMs. The space is moving very quickly. There are a lot of models being developed in this multimodal space. We have image to text, text to image, all of these kinds of varieties. Let's make sure that we're on the same page of what we're talking about when we're talking about what are VLMs and how they work. After we've got a good understanding of what a VLM is and how it's functioning, we're very pleased to show you all a demo today of a live integration of how a VLM in an annotation platform on Encore can look, and how to take advantage and use it in a production labeling application. After we've seen what's already here today, we want to talk about then what are some of the immediate implications of having access to VLMs in a production annotation platform, and also looking towards the future of applying VLMs in machine learning and computer vision development. So with that in mind, let's get started. The first question we want to answer: what are vision language models? Taking a look, what is a VLM? We've got a fridge, we've got a question, we've got a black box. Frederick, can you elucidate us to what's going on here?
Yeah. What we would like to be talking about today is these deep learning models where the interaction, it goes like this. You provide it with an image and some sort of instruction or a question. And then what this VLM can do is it can output a piece of text. Now, this figure might be slightly misleading here, as the fridge is now suddenly speaking and showing recipes and all that stuff. But generally, like the thing we care about here is image and text as input, and then you want to have a proper textual output. And that can be used for many different things. So, for example, like here, you can do stuff like figuring out what you're supposed to eat for dinner, or what you could eat for dinner at least. But it can also be like all sorts of other things, right? You could probably imagine how you could, have a visual assistant that would be looking you over the shoulder when you're fixing your bike, right? You could be asking it,
Mm-hmm.
how do I, replace the tire? And then
Mm-hmm.
it could tell you, oh, you need these kind of tools and you need to do this and that. Um, it's not really what we are going to use it for in this particular scenario, but that's basically the idea of these VLMs at a general plan. And obviously, going forward in today's webinar, we'll be sort of narrowing down the scope a little bit.
So taking, for instance, what you talked about here, I give it a picture of a fridge and I ask it a question, what I can make for dinner. I get some output. On the right side, it looks like, I see things such as what flavors you crave and a couple, maybe this looks like a snapshot from, Uber Eats or something similar. Does that mean these VLMs are also going to produce visual output, or what kind of output do we expect from VLMs in today's industry?
So at this point in time, what we have seen most is that they produce text. There are
Mm-hmm.
some scenarios. Perhaps you know interacted with some of OpenAI's models that can do multiple different things. You can chat with them and you can ask them to produce an
Mm-hmm.
image and these kind of things.
Mm-hmm.
We'll not quite be thinking about those yet, although it is
Mm-hmm.
definitely on the sort of technical horizon, both for like, I mean, it is available obviously in OpenAI and probably also going to be so in the open source community very shortly. So we'll restrict ourselves to text.
So just being clear here, then, there's all these generative models which have been, making waves in the press starting last year and continuing. DALL-E 3 is out by OpenAI. I think a new version of Stable Diffusion just landed maybe 1 or 2 weeks ago, where you type up a textual prompt about an image that you want to see. From a naive perspective, I'm starting with some text. I'm getting an image. Does that count as a visual language model?
Nope, not for today's definition of a visual language model. Although these models are extremely interesting and they can do some really cool things. It's actually what I studied. I spent a lot of time studying during my PhD, so I really like these models as well. But they're not quite within the scope. That being said, they do
Mm-hmm.
sort of rely on the same type of data to a large
Hmm.
extent. So what we'll be talking about a couple of times today is images and captions. Uh, and it's very relevant because the internet is full of images and captions, which is why we have been able to make so much progress in the field in the first place.
Mm-hmm. Mm-hmm. So then you're talking about this connection between images and captions. Let's go the other way, just for completeness before we move on. Going from caption to image, that is maybe a generative model, not a VLM. What if we start with an image and we want to break it down into a textual description? Where does that fall?
Yeah, that's also sort of in sort of a gray zone, very close to what
Mm-hmm.
we're thinking about. You're taking an image and you're producing a description. So it could be thought of as I guess, a subset of what we are talking about today. But the thing is,
Okay.
it's not really general purpose, right? It's a thing where
Mm-hmm.
it does one thing really well. It puts captions on images. While
Mm-hmm.
these like VLMs, they can do even more. They are, they're sort of general enough that you can ask them multiple different tasks to
Mm-hmm.
do the different tasks, and they will be able to perform them. If you asked a captioning model to do something else, it probably
Mm-hmm.
wouldn't work right. I wouldn't even know how to ask them in the first place.
Okay, then. So we kind of distilled all of the hype in the space, generative image models and digesting image models, image to text, and decided that we want to work with vision language model definition, which says, given an image input and a textual prompt, could be a task, a question of some sort, expect to have the visual language model do some useful processing and give a useful human-oriented textual output about both of those inputs.
Yeah, that is exactly what we want to be doing today.
Okay, so with a firm understanding of what we mean and the industry means by VLMs at this point in time, maybe an appropriate next step would be to look at how are these things put together.
Yeah.
So Frederick, we've got, looking at here, we've got, a cat on the left and a question, what is this? On the right, it sounds like the model is telling us it's a cat. But now we're kind of peeking beneath the hood. I see a visual model and a language model and some embeddings representation going on. Maybe enlighten us to how to interpret this particular graph here.
Yeah, I think I'm gonna start from the bottom left and move towards the right, and then just
Okay.
just for a second ignore the image and the visual model. So if you start thinking about an LLM, which is a
Yes.
large language model that most of us probably tried before, what it does is that it takes text, which is which could be like your question in this case, what is this? Then
Yes.
it does something called tokenization, which is basically breaking the text up into tiny pieces. Then for every
Mm-hmm.
token, it'll produce an embedding. So that's these embeddings we have over here. If we ignore the
Mm-hmm.
lang this part of the embedding, and then it'll have a decoder, which is basically one word at a time or one token at a time. It's predicting what's going to be next, and then it's taking that prediction and feeding it back into itself basically, and then continuously predicting the next word. That is how
Mm-hmm.
language models work.
Mm-hmm.
Um, and now if you are sort of a computer science kind of guy like I am, then you might think, okay, this sounds really slow. And like traditionally, it was really slow. And I can tell you, when I did my PhD, it was horribly slow. And I tried to do it for 1 pixel at a time. And I can advise you
Okay.
don't do that. That's where the autoregressive laws came from. Anyway, uh, story aside. So okay, so this is how LLMs work. Now, the big question has been like, how do you make LLMs also talk to images or like understand images? So the idea
Yes.
is that we just want to find a way where we can take images and turn them into the same type of embeddings as the text, in a sense where every
Mm-hmm.
embedding of a piece of an image and a piece of text, the goal is basically to have them be very similar if the semantic content is similar. That means
Mm-hmm.
that if I take the language model and I embed cat, and I take the image and
Mm-hmm.
I embed cat, I want them to be
Mm-hmm.
very, very similar. But then let's say I
Okay.
took I don't know, a giraffe instead of cat as either an image or a text, piece of text. Then the cat and the
Mm-hmm.
giraffe embedding, I want to be further apart from each other.
Uh-huh.
Okay. So there's this one very fortunate thing, which is that we already have language models that are really, really good and sort of understand human, text or human interaction via text. But we
Mm-hmm.
also have vision models that do that actually. So there's a model called
Mm-hmm.
Clip, for example, which is a
Mm-hmm.
model that understands how to do exactly what I just said. Take text and images and put them in the same place in the embedding space when they represent the same semantic content.
Mm-hmm.
However, this embedding space of the visual model, it doesn't align well with the language models. So now you can think of basically having, a Chinese guy and an American guy sitting next to each other and trying to speak, and they never learned each other's languages.
Mm-hmm.
So you somehow need some sort of translation between the two languages in order to be able for them to perform a task together very well.
Mm-hmm.
So that is the goal of this blue projection thing. It is
Okay.
basically the translator. And if you want to build your own VLM, or if we look at how, Lava, which we're going to talk slightly more about later, they were trained, then this is exactly what the first step is in like the vision, like teaching language models to speak vision. That's the first step. It is training this
Mm-hmm.
projection layer, the translator.
Mm-hmm.
So
Okay.
the way you do it is that you take the images and the captions, you map them through these two different components, and then you try to make the language model or the decoder basically predict the caption of the image. So you pipe the image through the model, and then you sort of compare the question you ask from the caption you are asking from the language model. You're comparing that against the actual true caption of the image. And if you do that a
Mm-hmm.
lot of times, then you can end up having a projection that understands how to translate.
Mm-hmm. All right. And so thinking about that there, then it sounds like you're relying on the strong foundational power of a language model and the strong foundational power of a vision model, such as CLIP. And then at the beginning of the process, CLIP and some large language model, for example, Llama or Vicuna or any of these, they don't speak the same language, quote unquote, until they're taught to speak the same language. And then you mentioned training the model. So the process of training a visual language model, which of these components are we actually tuning in order to get the best performance from our visual language model?
Yeah. We'll get back to this actually at some point. But the first thing you do is train the projection. That is what you're tuning. It's only this blue little thing. So you fix all the weights in the visual component and the language component. And then you just fine tune this projection thing. And the reason for that is that the only like, the way I like to think about it is like think that you have like two donuts representing the embedding space of the two different um, models, and then what you're trying to learn is how do I rotate and uh, you know uh, flip flip the one of the donuts to make it look like the other donut,
Mm-hmm.
or to align it with the other one. That's basically what it's learning. Um,
Okay. Okay.
yeah, and then when you want to go a step further, what you will do is instruction tuning, uh, which is
Mm-hmm.
sort of the next step, which makes the model able to, comply with certain, setups you might want. So for example, we'll
Mm-hmm.
get back to this a little bit at some point, but let's like imagine you're in the medical space. Doctors, they like
Yeah.
to speak in a very specific language. So it
Yeah.
would probably be a good idea to show the model a bunch of examples of interactions between doctors and images, or like big questions
Mm-hmm.
that might come in, and how doctors might ask questions about
Mm-hmm.
images.
So
So that's
we
some stuff.
can, pulling all of those things together, then a visual language model is actually several things that have to come together, both components and actions, and that you start with a strong foundation, visual and language. You then take a smaller, untrained projection layer, train it using the inputs, which is a cat, and a question, and the answer, which is this is a cat. Train your projection layer, which means a visual language model is as much a product of the components that you chose as it is the data and the training process that you went through, so that it performs adequately for the data that you put in or the tasks that you ask it to do.
Yes, that's I agree with that. That's exactly what I tried to say. Yeah, thank you for summarizing. That is, it's better than I can do it. Fantastic.
Well, this is a conversation here. So moving forward then into the next steps, given that this could be like a visual model and a language model or some of the fundamental components, does that mean that there's only one way to make a visual language model?
No, definitely not. There are very many ways, and there are very many models out there, actually.
Mm-hmm.
And one of the reasons why we can afford building a lot of different vision language models is that they're
Mm-hmm.
pretty cheap to train compared to the large language models. If you look at training Llama, which is the language component of some of these Lava models, it took like, I think it was like 6,000 GPUs for I think 12 days, like $2 million it costs to train that model. Now, this Lava model, it took like in the order of a day and 8 GPUs. So
Mm-hmm.
you can afford doing it a lot of times with different setups, basically. That's also why we see, for example, Lava having 4 different models where the language component it's different from model to model.
Mm-hmm. That's interesting to hear then, because you would think that, given that you're working with both language and visual components, these might actually be extremely expensive. But because we're relying on strong core foundations, we can actually train them to speak to each other at a relatively cheap cost, which is very interesting. And looking particularly at this slide, then we can see that some of these models are open source, some of them are closed, which means we know how the sausage was made, so to speak, or they might have other applications which make them particularly suitable to being introduced into other applications or annotation pipelines. Here at Encord, we're very happy and proud that we were able to integrate Lava 1.5 when it first came out back in October. And then, as everyone knows, the space is moving very quickly. Lava 1.6 was announced back in January, and 1 month after that announcement, we were able to bring that into the platform as well. Before we hop into what looking with a Lava integration might actually be like, Frederick, maybe it would be good to introduce a couple of the components that make Lava particularly attractive for something like being integrated into an annotation platform.
Yes, for sure. So obviously, when you want to put something in production, you want to make sure that it's to some extent battle tested, that you can basically rely on the code. And so this is one of the reasons why it makes sense to get something that is, for example, like partly released by Meta, some of the foundation components. And so that's one thing. It's really nice to have something that you feel like you can trust and has been used by many others. That's sort of a quality stamp. It's kind of like stars on GitHub, right? And then there are also other things that are sort of quite nice about Lava. And it's one of the things that I really like is the community around it. It's revolving really fast, but it also means that there's a lot of help to seek if you run into an issue that no one has seen before. Then an answer will be found not necessarily by you, but the community, essentially. And then there's also stuff like being able to use tools around it. For example, the Lava 1.6 came with a tool called siglang, which is an alternative to LangChain, for example, which is really, really powerful. and a lot of fun to use, by the way, if anyone out there like using or like playing with these models.
Okay. So now that we can see that there were a number of reasons, access to a community with everybody contributing plugins and improvements, as well as being able to see how the sausage was made and knowing that we're building on top of strong battle-tested foundations, as Frederick put, there were a number of advantages to bringing this into the platform. And we're happy to dive into what this can look like now. So give us just a second here to find out where we've got a couple of examples queued up. And Frederick, we're going to be counting on you to narrate through kind of the details of what's going on in the back end here. And here we go. I think we've got, let's go ahead and pop that one away. We've got, great. Frederick, let us know what's going on.
Yeah, so I think this is the most bare bone example of what I can show you that you can do with Lava in our platform. So this is a particular example where we are trying to classify images with the species of animals. So in this case, on the top left right there, you can see an ontology where you're supposed to answer whether it's like a dolphin or a cow or an elephant or whatever which is on the image. Then instead of clicking that button and clicking save, what you can do is you can ask Lava to do the prediction for you. And then you should get a response, which basically says, it's a monkey, which is on this frame. So that is all nice and good. And it's probably close to useless if you use it in this bare bone way, right? It's just to sort of give you the sense of, I defined something. I defined the ontology here saying I'm looking for animal species, and I can get an answer in return. So this is a classification answer. And similarly, you can do for checklists if you're not looking for one property within your image. You can do it for multiple. So now I allow the model to not select one thing, but select multiple things. So in this question, I ask, what does this image contain in the first place? And I think this is slightly more interesting if you like, for example, if you know what you want to label, or perhaps you have your first model already in production somewhere, and you know you're missing data with a certain property. Then you can use an ontology like this one and various programmatic ways to search the data for what you're looking for. So in this case, we could catalog this image with two tags, the bicycle and the monkey. Right. So then there's one more thing. I mentioned before that the internet is full of captions. So I can, of course, and that's one of the things that these visual language models are actually really good at, right? So I could also just ask for a caption of my image. That would be another way of just cataloging information in a more structured way than what is available just by looking at the image.
So how much information have we actually given Lava to work with here? It looks like we said image caption, and we basically have a free text field to fill in. What's going to happen here? What do we expect to pop back?
Yeah, so this is a very, very skinny example, I would say. It is basically what you can see with the eye here. You're asking for an image caption, and you'll get an image caption. But you could also imagine that you had a very specific thing that you were looking for. Maybe you're looking at CCTV cameras in a public space, and you don't care about, I don't know, something that is always like the trains that's always passing on this train station. So you could like explicitly ask the model to ignore that and then get only the sort of relevant details by sort of, changing your ontology and the way you query the model.
And while you were speaking, Frederick, it seems that our visual language model did come back with a description here. We basically asked for a caption, and it obliged. The image shows a group of monkeys interacting with a bicycle. That's pretty accurate understanding. There are 3 monkeys in the scene. Maybe needs a little bit of work here. The bicycle is parked behind a fence. The monkeys appeared to be curious and playful. So it's clear that the model is having a lot of understanding about what's going on. And maybe obviously there's still room for both improvement to the model and introduction into a full annotation pipeline process. But you get a lot of understanding with just one button press. But as you introduced earlier, Frederick, these are just the barest understandings of how a model can help us work with and understand our data. I think it'll be interesting to see that, particularly using some of the ontology capabilities on Oncord, where you can ask not just one thing, or multiple things, you can sort of ask a sequence of questions. Let's look like what it would ask. Let's look at like what it would look like to interact with the model in a more structured manner. So popping forward here, what's going on in our ontology over here? How do we expect this to work with Lava?
Yeah. So now the ontology, it starts with a question asking, does this image contain an animal? And then if you collapse the question again over there,
Yes.
you'll see like that's the only thing at the top level. That's the only thing we ask for. So we ask the model, and then if the model answers yes, then we will ask it or like prompt it with new questions. And if you expand the step, you will see that there are different sub questions. It's basically what we discussed before. It could be like checkboxes or like classifications or descriptions. Now, I have purposely made this ontology very, very slim again. In terms of context, I give it very little information. And in a situation like this, it doesn't work that well. And it's because that, like we as humans, when we label, we typically understand who we label for and what the task is all about. So we'll understand the context and we know what the question means, but the model might not know it in this case. So in the last tab, I know you have one more example open,
All right.
which is the
Well,
exact same task, but it'll be in a
yes.
much richer structure.
So to Frederick's point there, then even though it was lacking context, it still gave it a pretty good go. But with contains animal, that worked when the answers available were included explicitly monkey, or contains objects included explicitly monkey and bicycle. But as Frederick mentioned, this bare bones example didn't give the model enough context to choose a useful answer, and it told us no. And I think, Frederick, then if you can walk us through how we can work effectively with these models and how to have a rich interaction with them in this final example.
Yeah. Now, it's exactly the same questions. And we as humans would probably say that this is the same thing we are answering. But for the model, it'll be much more clear that when I ask, like, is there an animal in the image? It'll be more clear that I'm speaking about the image and I want one of these answers. And you'll also see in a bit, like the answers themselves also say, yes, there's at least one animal. It says, no, there are no animals. Similarly, I'll be asking for a more specific question for the image. I'll be, detailing more what I want. And so how I like to think about this is actually, it's like a conditional, prompting, like chain of thought kind of prompting technique that becomes basically visual instead. And I think that's where it becomes more powerful. I see there are, Justin, two questions in the chat. So one of them is basically asking about the medical domain. What happens if you ask about the medical domain and stuff, or like stuff like symptoms? And I think I'm not going to touch more upon it right now, but I just want to mention that we are going to be touching upon that slightly later. And the other one is actually also really interesting, which is basically I do not get the same answer every time I ask Lava. It's clearly someone who has tried interacting with these models, and there are ways in which you can do that. Like the obvious thing is reducing the temperature. So you basically enforce it to choose. I mentioned before that it picks one word at a time.
Yes.
You just want to force it to choose the one with the highest likelihood, most probable next word, instead of sampling.
So moving from that there then, from that expression, and also what you mentioned earlier, just a couple of sentences ago, Frederick, you mentioned, chain of thought and correct prompting here. While we were speaking, it looks like Lava gave it a go at actually thinking about what happened here. So I'm going to flip over to the frame labels. Looking through the ontology you put together, you guided Lava through a chain of thought and sequential questioning where you said, is there an animal? Yes or no? If it's no, then the buck stops there. But if it's yes, then tell me a little bit about what's going on. And we'll see what we got back compared to our previous example. Pop on this. We'll slide this up so this is much clearer for folks. Is there an animal? Yes, there is at least one. What other entities are the animals interacting with? Well, they're interacting with other animals. That looks fair. We can see there's a bicycle in there. There's mostly monkeys, and we're getting a description. Frederick, you mentioned chain of thought, but also particularly in this, we can look at this at one level as a nested ontology, but these are also questions that couldn't be answered until you knew the answer to the previous one. How does Lava approach answering these questions that build onto each other in sequence? Does it answer everything at once and do the full computation, or does it answer the first one and use its first answer to answer the second one?
Well, I don't know the internals of Lava, I must admit, so I cannot answer on its behalf. However, I do know how it works in our platform because I basically built it, or at least some of it. And so in our situation, what we do is we do it conditionally. So we look at what is the answers on the top level, and then we go one level deeper, look at what are the answers, and then conditionally route, obviously both to sort of save compute, but also do the compute necessary. Yeah.
That's
so it also
excellent.
means that you won't be collecting these false positives. If there are no animals, you won't be answering these, collecting these answers.
So we wouldn't have a situation then where it would say, no, there are no animals, but it's trying to interact with a bicycle because of how we've constructed this question and answer sequence.
Yeah, that's exactly right.
Okay. So very happy to show everybody what's possible today here in the platform. And I think this is also a great example that Frederick constructed for us because it shows at least two relevant areas to anybody who's interested in building these production annotation pipelines and working with foundational AI, in that the different contexts that you have when you're working with human annotators versus computational annotators, and that when you work with computational annotators, you have to provide the correct context at the correct time in the correct sequence. And then you can scale those questions using automated abilities such as interacting with an SDK and feeding in your data, et cetera. But you also have to monitor that output. And then another point, which was great also to see in this then, is that making sure that you give it the right task, that they feed into the next question or that they feed into the next answer, is how you can ensure that the model does the most amount of efficient work for you. If you ask a lazy question, what's here, you'll get a lazy answer. I don't see anything. But if you ask an appropriate question, what are the animals here? What are the items here? You'll get exactly the answer you're looking for. And Frederick, it's very interesting to see how we constructed sort of the sequential complexity here and how much you can really get out of these models when you know how to speak with them. Now that we've seen what the models can do in the platform already, I think it's interesting to kind of take a quick step back and imagine how these can be used in annotation pipelines and workloads right now, and then also how we want to use VLMs going forward in the near future as well. So let's move on over and cut through the agenda here for the final section of the webinar. So looking at this then, we have our fuzzy feline friend is back, but now we realize that we can ask more than just what is this? We can also ask which of the animals from this particular list I've given you are present, or you can ask a confirmational question. Is this a dog? This means that previously we showed that these models can play a role in pre-labeling or auto-labeling, if you will. I saw a cat, but they can also play a role on the other side of the annotation pipeline. Maybe you're doing validation. Was there a cat in here? Was there a dog in here? And it can give answers and help play a role on the review part of your pipeline as well. We can also see then that we're having a transformation fundamentally from unstructured visual data to structured textual data here using these VLMs. I think something that might not be obvious is the implications of this structured image retrieval, particularly when we're getting just a very simple one-word answer out of here, like cat. Frederick, what are some of the ways that people might be meaning? It's nice to get a bit of text out. There's a cat, or it's not a cat. But when we structure this information in particular ways, what are sort of the implications of how we can use these in other processing pipelines?
Yeah. So one thing is that if you, I think I kind of alluded to this earlier, but one thing is if you're missing data of a certain with a certain property, if you have cataloged data based on properties you're going to be looking for, then although I know you said before that you'll get exactly what you're asking for, where I'm a bit suspicious about the exactly. It is a machine learning model, and machine learning is almost by definition not perfect. I'm not sure about the definition thing either, by the way. So it's probably not going to be perfect. There will be false positives and there will be false negatives. But as soon as it is better than random, then it means that you can narrow your scope every time you're looking for something. That's where I think it's particularly valuable in terms of structured. And I think the next slide will also show it a little bit more in a second. But I think the structured information can also be, because it can be conditioned, as we saw before, it will be more relevant than just doing a natural language search with Clip, for example. I don't know. Some may have tried that.
Okay. I really liked then the framing of that, because we know these models aren't perfect. We know machine learning in general isn't perfect, setting aside greater philosophical questions. But we know that they're much better than random. Ergo, it's doing useful work to narrow scope successfully and make it easier for us to decide how to prioritize our work going next, which leads obviously in to where we're seeing a lot of interest and looking into ourselves is using these models in what could be pre-labeling or auto-labeling, and more than just sort of content questions. What is there? I think there's a number of interesting possibilities that we're investigating and that people are looking into at these more advanced levels of conditional reasoning. Frederick, maybe you could walk us through, at least 3 very interesting types of conditional reasoning beyond binary presence that these models could help us with.
Yeah, I think if we read these questions and answers in sort of sequentially, it would be sort of first you are asking for something like, what is the apple that is outside, right? And then you get an answer. It's the upper right apple. Okay, that seems correct. And then you ask it for the color. Now, this second question, it can actually be you don't necessarily care about the model's output to the color, because you can compute that in other ways where it's accurate, right? We understand color very well. So if you know where the apple is in the first place, then you can answer that actually yourself. But it's interesting because the model will gain that content or context before answering the last question, which is, is it ready to eat this apple or not? So it's very toy example here on ways in which you can sort of pre-label your data in a conditional way where you are at least on the right track in terms of finding properties that you are on the outlooks for.
So I think this is really interesting that you managed to put this together, because it demonstrated not only the sort of chain of thought that you brought up earlier, but how the chain of thought combines almost at a human level in terms of doing spatial reasoning. And then we allow it to discover something we already know, such as color, purely so that it itself has that context and can give you further information that could be useful to humans, such as, is this apple ripe for the eating or not? I mean, this could be a green apple. There's a lot of context that could be missing, but it shows how to have useful high-level dialogues with these models about visual information. And this is something that we're seeing possible with the models out there already. Moving on, and we have seen a number of these questions coming in from folks. So I think we're very happy to be getting here. Is of course, how do you work with these models in particular domain-specific areas? We saw how they worked, identifying monkeys and bicycles or apples. And Frederick guided us earlier, telling us that we built these visual language models on strong foundations of these large language models and these foundational vision models, which are trained on huge corpuses of data available on the internet. What do we do in the cases where this data isn't so readily available or isn't as readily reliable?
Yeah, I think there's a really cool war story that I just wanted to put a few words on. And I see there are a couple of questions in the chat about geometries like bounding boxes and masks around pre-labeling as well. So I just want to make sure that we set aside at least a minute or so for that. But maybe, I don't know what you prefer, but
well, let's roll back and see if we can hit the geometries at this point, and then let's roll forward into the domain-specific applications.
Yeah. So on the geometry side of things, we have seen some development for these VLMs in terms of also being able to understand geometries. I don't know if you tried it ever, but if you ask GPT Vision for a bounding box around an object you care about, it'll just refuse. It doesn't like to do that. It'll just say, I don't want to do it. I think it's even been trained to not do it instead of trained to, yeah. But there are models out there that do seem to understand it. And I think it's something that we won't have to wait that long for. There are different ways in which you can do it. Actually, the image we see on this particular slide, if you notice, it has like these bright colors around every apple. And it's actually from an experiment we did where we took all the apples and then we asked, first we asked SAM, which is this segmentation model that doesn't understand classes and classification labels. Then we asked to, segment everything in the image. And then we shipped this image off to GPT Vision along with the numbers, the black boxes on the apples, and asked for every number, what is the class? So that's one way you can actually do it already. And it works surprisingly well. So things are coming, and I think probably the secret sauce will be the sort of glue that sticks together models in the end. That's probably going to be the winning one. But there's also another model called Quinn, which came out a couple of weeks ago, that has also been fine-tuned with instructions around geometries. So we will see it. It'll not be years away. It'll be shorter than that. Is my best guess. Yeah, I hope that answered at least some of the questions.
It answered some of mine. I did not realize GPT Vision was actively turning down bounding boxes, but I'm looking forward to when we get the bounding boxes from these visual language models. Okay, let's roll forward into the next one, which I can see a lot of interest from folks with as well. So we asked the question, what do we do when we don't have huge amounts of training data available, or we do have training data available, but this wasn't how the models were originally trained to behave?
So the war story I was talking about before is about a model called LavaMed. And LavaMed is sort of a symphony of all the things that have also sort of come up in the chat, which is basically, do I need to fine-tune clip? If it's domain specific enough, yes. So LavaMed is based on a visual backbone, which is called Biomed Clip from Microsoft. And that was pre-trained on, I think, 15 million images and their captions, all collected from medical publications. I think it was basically what's it called? PubMed, I think it's called, this publisher. Yeah. So first of all, you build like a visual backbone that understands medical lingo. And then you also need to align the two things. So train the projection thing we were talking about, the blue box, the blue blob we were talking about earlier. So that is what is shown here in stage 1. That is this concept alignment. And then furthermore, you want to make Lava speak, and maybe I should say that was done with like 600,000 samples. And a sample here means an image and a caption. So there are no instructions yet. And then to make it, act like a doctor, you also need to do instruction tuning, which is the last part. And that's only like 60,000 samples. But these 60,000 samples, for those, the data quality is of extreme importance. Now you really need to make sure that what you showed there is also how you want it to behave. You sort of want to have this final model. And it turned out to beat all the other domain-specific medical models in, for example, visual question answering. VQA, as it says on the right there. Yeah. That's sort of one really cool example.
So pulling that together then, Frederick, it sounds like the important part here, because 60,000 samples is not normally considered a lot by the scales of large AI. But you mentioned that it really comes down to, first of all, tuning this projection layer that we saw in the earlier component diagram. There's a visual model and there's a large foundation model, and then there's a projection model. And so this medical concept alignment takes some large amount of samples, but I don't think many people would consider it large by foundational AI standards. And the data then is critically important, not the volume, but the quality at this fine-tuning task stage. And then you also introduced, there was, depending on sort of the scarcity or the rarity of the data, there might be a hidden stage 0 here, which is Lava is built on CLIP, for example, which translates common everyday concepts into a text embedding space from images. But if you want to do the same for medical data, which might, rely heavily on X-rays and black and white images, things like that. You want to make sure there's enough space in your embedding space to adequately represent these different concepts, rather than the same kind of things which would tell apart a monkey and a bicycle.
Yes, that's correct. And I believe actually also that the language component was medical specific. So you can of course do the same trick on the language model. I think it was called MedBird, something like that. So it was like also taught to speak doctor, basically.
So start here at the concept alignment and at the task fine tuning. And if you find that at the foundations, you need to add a little bit of power, you can step backwards a step at a time and retrain at the foundational level as well. Noticing the time here, I think we probably also want to move on and look towards the close. Frederick, did you have a final point there?
No, it was just a little drop, which is basically, if you notice once in a while, they say that they give you a base model. It's because the model was only pre-trained and not fine-tuned.
Yes.
So that's when you go back to stage one.
Gotcha. One of the other items that we wanted to address, we're going to try and keep it brief, obviously, given the time, but we see a lot of interest in using these models to address how they could work in video data. And it's interesting then, going back to that previous slide, what we're doing when we're working with video data is we're really working with temporally sequential data. And it means then at these levels of fine tuning and task tuning, we're teaching the model to recognize how concepts it already knows are related in time, which means you can feed it a data set of images that would appear over time and ask it questions or useful interactions and tasks that rely on temporal knowledge and guide it with those answers. So you could teach it to recognize a sunset by feeding multiple images of a sunset and asking it what is happening to the sun in this image, and obviously training on the answer, this is the sun setting, because it knows all of these concepts and then simply needs to learn the temporal relation. One final area we wanted to visit before wrapping up a very enjoyable afternoon with you all was just looking at how these models can be deployed, not just in giant data centers, but also closer to where the inference action is, as it were, and some of the interesting techniques that are going on and developments in this space to bring VLMs to the edge. I see a llama rocking the coolest pair of shades on here, but Frederick, maybe it would be interesting to talk about what's going on with Grok, and perhaps what we mean when we see these models going from big to small so that they can be deployed at the edge.
Yeah. Deploying at the edge is, I guess, it's basically where the real value lies, right? If you can make these things run fast and give you good answers in sort of a way where you can feel like it's an interaction where you're not waiting, that's where the magic lies. And so that's obviously what a lot of people are trying to do, and they're doing it on very different levels. So Grok is one of them, right? Most of you probably saw it already. Like, it's been all over social media. They're able to run these models really, 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 really fast, like 300 or sometimes even 500 tokens. And a token is like, you can basically think of it as a word per second. So that means that it can write so fast that you can start really using it. And they do it mostly on a hardware/compiler level, where they have built some hardware that are very well suited for this particular task. I don't want to put my head on the line, but I think it might not be Turing complete for those of you who are. Anyway, and then there's of course also a bunch of other things you can do. So, for example, on the software level, you can, I don't know, mask what you allow the model to do. If you are particularly looking for a JSON, you can filter the outputs in a way where it'll only consider valid JSON outputs, and then it'll be much faster, 5x, I think, roughly. So there are all these sort of different things you can do, and you can also, distill models or train smarter models on higher quality data, all these different things to try and make models that are as capable as possible, but run as fast as possible.
And one final bit here to end up this enjoyable discussion. I've been really intrigued by what people are talking about in this model distillation. Obviously, we saw in our earlier slide with Lava, there was 4 different varieties of that language model where it's 35 billion parameters, or maybe it's 13, or maybe it's 7. What work is being done, or can we do to make these models smaller but not lose too much in performance?
Yeah, there is, like, for example, model distillation you can do where you have basically a big and a small model, work with each other. The bigger one is going to
Mm,
show the smaller one how to behave, and then
mm,
the smaller one will sort of learn to behave as the bigger one. So it's like a teacher-to-student relationship. You can also
mhm,
use the big model to curate your data set to get a higher quality data set, and then train a
hmm,
smaller model on that data set. So
mhm.
there are sort of various ways in which you can do this. Another
Uh,
way I saw, like, it was released 2 days ago. Another thing I saw was that you can also take all the weights in your model and then represent each of them with only 3 bits.
uh-huh.
That's another way. So no, sorry, 2 bits, I guess. 1.5. Anyway, so every weight can only be like -1 or +1 or 0. If that's true, it's completely insane. Um,
Big if true in the most real sense. Okay, and before Frederick lets us run away with the entire afternoon, I think
Sorry.
this is probably where we have to. No worries. I mean, we came here to talk about AI, and we talked about AI. It's enjoyable, but we do have to, I think, keep in mind the time for ourselves and obviously for the participants. Looking towards wrapping up here, I think very happy that so many of you were able to join us this afternoon, and very much enjoyed the engagement from many of you during the webinar. Hopefully, we were able to address a number of questions over the course of these items. Otherwise, we received a lot of very interesting engagement from the attendees. Very excited to to be reaching out to some of you, and also you can always reach out to us. And just wanted to quickly plug that we have another webinar coming up soon. And if you enjoyed this, obviously join us again in a month to learn a lot about medical imaging and annotation with 3D annotations. Otherwise, Frederick, thank you so much for walking us through all of the exciting developments in the space. Hopefully everybody saw and had their imaginations set alight with all of the things that we can do already and all the things that we're looking forward to. We're looking forward to building amazing AI applications with all of you, and we'll talk to you soon. Thank you very much all.